Hey, this is cool stuff, man. Hope you like it. So, my name is Dr. Harvey Miller, and this is our third installment on the chapter that deals with process strategy. And in this particular installment, we are going to focus on doing things like break-even analysis to kind of help us determine at what point a process will actually um, yield sort of or break even so that we know if it makes sense to even consider that particular process. If your demand is much less than the break even point, you might say we need a different process. But if your demand is much greater than that break even point, then you know that you will actually achieve some benefit because you will have to produce more than the break even point, in which case you can make a decision to go ahead with that particular process. So we're going to use the concept of expected monetary value, net present value, break-even analysis. These three tools to kind of help us in making process decisions. You've done some of this, I believe, in your Introduction to Quantitative Methods course, but now we're actually seeing its application in the context of operations management. So let's focus on break-even analysis. But just before we do that, what we're going to cover, as I've already mentioned, is break-even analysis, reducing risk associated with incremental changes, applying expected monetary value to capacity decisions, and applying investment analysis to strategy-driven investments. All right? So we'll learn a little bit about breaking even. We've already done the sort of bottleneck analysis, but computing a break-even point and expressing that in terms of units and money, net present value, just sort of reminding you of that and how you compute the net present value of an investment, because most times when we are spending money for capacity, we are thinking about whether or not the investment that we're making is going to yield benefit to the organization. We talked about theory of constraints in the last case, in the last presentation, but I'll just repeat it here since I have the slide up. So the whole idea behind theory of constraints, just to remind you, is that all processes have a bottleneck, and if you want to improve the process, you have to focus on eliminating the bottleneck. Once you've eliminated that bottleneck, you're now resetting your process performance, and if you're not satisfied, you continue the process of examining and looking for the bottleneck. Once you find a new bottleneck, then you have to apply resources to eliminate that and continue this continuous improvement process. Okay? So you identify the constraint, develop a plan to overcome that constraint, focus resources on accomplishing step 2, which is to basically overcome or eliminate that constraint, reduce the effects of constraints by offloading work or expanding capacity. Once you overcome that, go back to step 1 and find new constraints. So it's a continuous cycle. All right. In terms of managing bottlenecks, some of the things that we can do is to release work orders to a system at a pace that basically is consistent with the bottleneck. So if your bottleneck is like 5 minutes, then release work to the system every 5 minutes, since a product will emerge every 5 minutes. What that does, it avoids work in process inventory. Because remember the example I talked about in the last presentation, that if you have a workstation 2 minutes and 5 minutes, and you put in every 2 minutes, you put in raw material, what happens is that when that raw material is finished in 2 minutes, the workstation that processes in 5 minutes is not ready yet for that. So it has to sit and wait until the remaining 3 minutes is done, and then it can be processed. So if you want to avoid that, every 5 minutes release an item into the system. What that means is that you will end up having 3 minutes of idle time at the 2-minute workstation. It means that because you want your total amount of time every in that workstation to now become 5 minutes, right? So what you do is that you know that it processes for 2, so you're going to have to wait for 3, so that you get that 5 minutes flow into the system. If that's fine with you, hey, then that's okay. But if you want that machine to be working constantly, then be prepared for a build-up in your working process inventory between that workstation that processes at 2 minutes and the one that processes at 5 minutes. All right. Lost time at the bottleneck represents lost time to the whole system. Increasing the capacity of the non-bottleneck station is a mirage. In other words, don't focus on the workstations that are not bottlenecks, because you're not going to get any benefit from it. Increasing the capacity of the bottleneck station increases the capacity of the entire system. So these are just some basic principles to keep in mind. All right. So break-even analysis. I think most of us have done break-even analysis, or at least understand the concept that is, if there's a fixed cost and a variable cost, and then we have a price that we're selling a product for, then we could determine the point at which we're break even. That is when our revenues actually matches our costs. And then we could actually compute how much we need to sell to break even. And if we need to sell more than the demand, that's a problem. If the demand is much more than what we need to sell to break even, then we are in a good place. Okay. So fixed costs are the costs that continue even if the new units are produced. So the fixed costs associated with equipment. Sometimes your fixed costs have to do with your utilities, labor. If your staff is idle, you still have to pay them a fixed salary, etc. Depreciation, taxes, mortgage payments, and so on. Variable costs are the costs that you vary with the volume of units produced, labor, materials, proportion of utilities. Well, in the case of the labor part, if people are not on salary but actually paid in accordance to the number of pieces they produce, then that's called a piece rate. In which case, yes, so the variable cost will change depending on the number of units that you produce. Not the variable cost, but your costs that's linked to the variable cost will change. So that you would not include that as part of your fixed cost. Contribution is the difference between the selling price and the variable price. So the contribution, or your gross margin, if you wish, is what that will help you recoup the cost. And when you sold sufficient amount to recoup that cost, after that it becomes profit. Okay, so let us look at some assumptions in terms of doing break-even analysis. Costs and revenues are linear functions, generally not the case in the real world. We actually know these costs, very difficult to verify, and time value of money is often ignored by this particular process. So as you can see, we have the number of, if we look at this function, the total revenue line is this line right here. So our revenue. But then with our costs, we have a fixed cost and a variable cost. I didn't draw that properly. There you go. So of course, if we look at this bottom part right here, we see that our revenues is actually lower than our cost, right? So in this portion right here, revenues is lower than cost, so therefore we're incurring a loss. And then at the point where our revenues is equal to our cost, that's where we're breaking even. And after that, this is where you get into the profit corridor right here. All right. So always make sure that if this is your break-even point, X star, that your demand is greater than your break-even point. Cool. All right. So how do we compute? How do we do the break-even analysis? It's not hard to do. If you recall some of what you did before. So break-even analysis in terms of units, so we could call it break-even point X, and then we could also be interested in the break-even point in terms of dollars. What does it mean in terms of dollars? So I need to just hold on a second because my my iPad is not streaming right now. It's now streaming, so let's see if I got it back. And so you have to just bear with me for a second while I get it streaming again. Alright, so don't go anywhere. Sometimes I guess maybe it just gets tired, you know. So there we go. So we are looking at break-even point analysis. So the break-even point is given, and we're given this function here. But let me just sort of do it for you so that way you can see how it comes about. Well, the break-even point happens when what? When our total costs is equal to our total revenue. Cool. So in this case here, what's our total cost? If we're using functions like F is our fixed cost, P is our price, let's say C is our variable cost, unit cost, and X is our production quantity. Alright, so in that case, what's our total cost? Our total cost would be our fixed cost plus the variable cost. Let's make that VC just to be consistent with the text, times X, the amount we produce. Our revenues would be the price times X. So if we solve for X, then we would get F divided by P over minus VC, the variable cost. That's, in other words, we are trying to recoup the fixed cost from the contribution or the gross margin, if you wish. And so that will give us our break-even point. Now, if we want our break-even point in dollars, we multiply the X by P. So your break-even point in dollars, so BEP dollars is X times P, right? So we know that the break-even point is F divided by P VC. So we must also multiply this by P as well. We're multiplying both sides by P. If we multiply both sides by P, we could bring the P below here as a denominator to P minus VC. It will look something like this. So your break-even point in dollars would be F over P minus VC divided by P, which then gives us F over 1 minus VC over P. Right? And there we go. That will be our break-even point in dollars, and our break-even point in units is actually up here. Cool. So let's see. I've already just shown you that. Let's look at this example. The firm first determines that it has fixed costs of $10,000. Direct labor is $1.50 per unit, and material cost is 75 cents. So of course we have to add those to get our total variable costs. Our variable cost would be, so your variable cost would be your 150 plus 75 to 25. Okay. Good. The break-even point. So if we want to just get the break-even point, as you can see, in terms of actual quantities, first of all, we should say that break-even point then X star would be equal to the $10,000 divided by the price, which is sold at $4 per unit, minus $2.25. So that should be 10,000 over $1.75. Whatever that turns out to be is the answer. All right. If we now want to compute that in dollars, then we would say this is F, remember, over 1 minus VC over price. So that's your BEP in dollars, which is 10,000 over 1 minus $2.25 over $4, which gives us 10,000, and I believe when we compute that, it turns out to be 0.4375, as we could see up here. All right. So what are the answers to this? In terms of our break-even point, in terms of units, it turns out to be 5,714. To convert it to dollars, we simply have to multiply by $4. 4 5s are 20. And then if we go back to here, we'll see that it turns out to be 22,857.14, right? So all you have to do is to just multiply this by 4, and then you get that same answer that you just see over here, 22,857.14, 22,857.14. You could do the math yourself, all right? Excellent. So that's how you do break-even point. It's fairly straightforward. Now, reducing risk with incremental changes. Remember, I had a little discussion on that in the last video, where we talk about the idea that we could balance our capacity changes with our demand changes in our demand. So here's a case where we have to think about what are the risks associated with how we change our capacity. So in this case, we are going to introduce capacity ahead of the demand. So this is we're going to be leading the demand with incremental expansion. And what's the risk of that? Well, there's a possibility that the demand does not increase and then we're stuck with excess capacity. Right? There's a risk here. And this is the excess capacity that you would have in each case. Right? So when the capacity meets the demand, we ramp up the capacity and so on. Now, can we ramp up capacity that easily? Probably not. We probably have to ramp up capacity like this. In other words, the slope is actually different. It's not straight up, and so this is where we might actually have this, and this would be your excess capacity. In that case, like I said, the major risk has to do with you being very optimistic. Turns out that the capacity doesn't quite turn out to be what you want, and therefore there's a risk associated with that. So you could leading demand with a one-step expansion. So rather than, so the idea that you introduce new capacity, and over a fixed period, and you sort of just observe that this is your expected demand. And but you will over time have to consider the decision of whether or not you're going to increase your capacity. Here's a case where you actually decide, well, I'm going to take my time, wait and see, and incur some losses first before I actually decide to increase capacity. So in this case, this is where we started. Now we're here. In other words, we keep the capacity at this level, then we expand, keep the capacity, then we expand, and so on. And in so doing, there's a risk that you will incur shortages because you do not have enough capacity to meet the demand. It all depends on what's the cost of a shortage. What's the cost of being short? Are you going to lose customers that you could never regain? Or is it a situation where you may very well have people on back order until your capacity has actually gotten to the point where you can meet the demand? It's a risky situation as well. And this one is a combination of both. You try to average out your capacity where you're straddling cases where you exceed the demand and then cases where you're below the demand. So as you could see here, when this line is in the middle, you build some excess capacity here, but then you're willing to incur some shortages here. And is this a good strategy? It all depends again on what's the cost associated with being out of capacity. What is the opportunity that lost from not having sufficient capacity? And you have to balance those. It's not easy to say ahead of time what it is. You have to do the analysis to determine which of these strategies are actually better. All right. Here we want to look at this idea of expected monetary value to a capacity decision. Sometimes we are at a point, and this is where we use some probability analysis. We're trying to make a decision. What are the options that we have for us? So we could say, if we decide we're going to have three possibilities. For every decision that we make, so this could be, let's say we're thinking about expanding the capacity. We could say, hey, no, stay the same, no change, same capacity. And any decision that we make, there are two possible outcomes, not three, but let's say two in this case. And actually I think I drew these the wrong way. So here's our decision node right here, and then we have our probabilistic node right here. We're going to consider three options. Okay, instead of saying we're not going to do anything, we're going to say small, increase our capacity, small amount of increase in our capacity, medium, and large, for example. And what happens is that here is you have a probabilistic event. So the two outcomes are the demand could end up being high or the demand could end up being low. The probability of the demand being high is 60%, 40%. If we have that information, the next example you'll see uses those. But I just want to kind of map it out so that you can see how we're thinking about this. So this is our decision point. We were talking about capacity decision, right? What capacity? Small, medium, large. And then the probability of the demand doesn't change. And the probability is associated with large demand, small demand, 0.6, 0.4, 0.6, 0.4. However, the profitability or loss for each of those situations can be different. So, for example, it could be that if we build small, right, and the capacity and the demand is high, so this is high demand, low demand, high demand, low demand, high demand, low demand. Well, let's say we make $10,000, but then if we only $5,000, let's say $3,000. Then if we go medium, we could make maybe $20,000. But then there could be a loss of $4,000. And then if we go here, we could make about $50,000. But then there's a loss of $15,000 if the demand is low. So now we're trying to determine what do we do in this situation. So what you're going to end up doing is the one that has the best expected monetary value is what we will actually choose. So do we choose, let's call this one A or small, B or medium, C or large, right? And so at this point, we want to determine the EMV, the best expected monetary value of our decision. And how we do that is by computing an expected monetary value, which would be the probability, right? P1 times the outcome associated with thing. So P1 times the outcome 1, plus P2, the probability times outcome 2. Right? If there are 3 outcomes, you go plus P3 outcome 3. So for example, the very first one, EMV1 or EMVA, would be 0.6 times 10,000 plus 0.4 times 3,000. So that's basically 6,000 plus 4 3s are 12 plus 1,200 is equal to 7,200, right? If we're looking at the second one, EMVB, then it would be 0.6 times 20,000. But because we're losing, it would be minus 0.4 times 4,000. So 6 to the 12, so that'll be 12,000 minus 4 4 is a 1,600. That's actually 10,400. So as you could see, that 10,400 is already better than the 7,200. And last but not least, EMVC will be 0.6 times 50,000, I think I said. And we're 0.4 times 15,000. Right? Notice it's negative because we are incurring a loss. So that would be 6 5s are 30,000 minus 4 by 15 is 6,000. So that would be 24,000. All right. So when you look at these 3 options, the one that has the highest monetary value is C, for an expected monetary value of 24,000. So if we're going to use the criterion where we're going to maximize our expected monetary value, then our decision would be as follows. We would not go with this guy, and this is expected monetary value of 24,000, which is decision C. That would be our decision right here, all right? So that's how you would use expected monetary value to conduct your analysis. And this is an example given to us applying expected monetary value to capacity decisions. So I will let you go through that yourself, but let's just read the context of it. So the approach is Northern's major alternatives are to, this is a hospital. Northern's major hospital supplies, a company that makes hospital gowns, is considering capacity expansion. So its major alternatives are to do nothing, build a small plant, build a medium plant, or build a large plant. So if it does nothing, it's not going to lose anything. Nothing's going to change. The new facility will produce a new type of gown, and currently the potential marketability for this gown is unknown. If a large plant is built, a favorable market exists, the profit will be 100,000, right? Could be realized. An unfavorable market would yield 90,000 loss. However, a medium plant would earn 60,000, right? A 10,000 loss would be the result of an unfavorable market. A small plant, on the other hand, would return 40,000, favorable market, but lose only 5,000 in an unfavorable market. Of course, there's always the option of doing nothing, Recent market research indicates that there is a 0.4 probability of a favorable market and 0.6 of an unfavorable market. All right. So use your expected monetary value approach to solve this problem. And you could see here for each of these situations, for the large plant, if we look at the values, so 0.4 times 100,000, 0.6 times minus 90 gives us a loss of 14,000. So you definitely don't want to go for a large plant. Nobody wants that. That doesn't make any sense. However, if you go medium, 60,000, positive, market, and then loss of 10,000, and that gives you a net value of 18,000. And then the small plant gives you a net value, MVA, expected monetary value of 13,000. So according to this, it makes sense to go with our medium plant. All right. So that's the decision. I just showed you the example of how we do that. So operations may be responsible for return on investment, ROI. So we have to give that consideration when we do our analysis. Analyzing capacity alternatives should include the capital investment, the variable cost cash flows, and net present value. So if we have the information on the cash flows and the interest rate, we could actually compute the present value if we assume a useful life for our investment. So we may have a series of cash flows and then say maybe we want to assess this on a 10-year time horizon. So if you could have estimates of cash flows for 10 years, then you go ahead and you would be able to do the net present value of those cash flows. All right. So here's the basic formula. The future value of an amount is F is equal to P, which is the present value, times 1 plus I, which is the interest rate, to the power of N, where N is the number of periods or the number of years, such as 1 year, 2 years, 3 years, 4 years, and so on. All right. Typically, we use interest rates of about 5%. And in this case right here, if we're talking about the future value of $100, at the end of 1 year, it should be worth $105. If we then say 2 years, then it will be worth more than that, right? So it all depends on, we're compounding the interest, because we're making the assumption that the interest is reinvested. If we want the present value, then we could just simply rearrange that formula where we say the present value is equal to the future value divided by 1 plus I, the interest rate, to the power of N. And so we could actually compute that. If we want to determine, if we have the factor tables that gives us, because sometimes if we don't have a calculator to do the exponent, then certainly we could actually use the factors in a table based on the interest rates and the number of years, and then we could actually get a factor that we could use in our function. All right. So here we go. If we consider F is just a single dollar future value, we get the present value from 1 over 1 plus I to the power of N, depending on the interest rate and the number of years that we're thinking about. So here you go. The number of years, the interest rates over here. Oops. Number of years and the interest rates, and that then gives us the information that we require to be able to compute the present value of a future amount, right? And we could certainly use that. Limitations in using those, making those decisions around investments, is that sometimes you could have an investment with the same NPV, but their projected lives can be different. So you have to think about that. And also the salvage values. In some cases, they may have different cash flows, and one cash flow might be preferable to another. So you want to look at the cash flow stream to see which one is better. What if you have an investment that have sort of low cash flows in the beginning, but high cash flows at the end? That can end up being very costly to you, where you have some losses in the early stages. Or if the reverse is true, you may want maybe balanced cash flows. It's up to you. It all depends on the nature of the nature of the business that you're running. So the point is that you have to consider the differences in terms of what does that cash flow stream mean to you, and what is the ideal form that it should have. All right, you don't want everything bunching up late in the later years and you having major losses in the beginning. Some cases that's preferable. Some people want to write off the initial investments. Payments are not always made at the end of the period. So these are just factors to consider, and assume that we know the future interest rates, which could actually change on a day-to-day basis. All right. So capacity calculations and capacity planning is essential for profitable operations. Other considerations are accurate forecasting, understanding the equipment and the processes and the capacity increments that we want to consider, finding the right operating size so that way you have balance between your capacity and your demand, ensuring that you have flexibility to grow or to actually shrink your capacity if your demand pattern changes, if the demand for new products introduced and so on, is introduced. So these factors actually matter, and understanding the bottleneck and break-even analysis are also useful techniques. Bottlenecks help you improve the capacity of a process. Break-even helps you make the choice between processes. And then, of course, expected monetary value helps you as well with the decision around capacity expansion options based on financial calculations. All right? So this has brought us to the end of our chapter on process strategy. The process that you use has implications for your ability to achieve your mission and your vision and to meet customer demand. So it has to be given due consideration to ensure that your capacity strategy creates value for your customers.